In January 2026, NASA confirmed the most distant galaxy ever measured, a smudge of light called MOEM-Z14, sitting at a redshift of 14. 44. Its light left home just 280 million years after the Big Bang and has been crossing space for roughly 13, 5 of the universe's estimated 13. 8 billion years to reach us, that single number 13. 8 billion is the one you've heard your whole life. It's in textbooks and documentaries on the wall of every planetarium. So when headlines this year started claiming James Webb had caught the number changing, a lot of people understandably wondered if everything we thought we knew about the universe's birthday was suddenly wrong. It isn't, but the real story underneath those headlines is stranger, more contested, and more scientifically important than the clickbait version, and it deserves to be told properly. Let's start with where 13, 8 billion years actually comes from, because almost nobody explains this part. Scientists don't count backward like a calendar. They measure how fast the universe is expanding right now, then run that expansion rate backward through the equations of general relativity until everything converges to a single point. The number that falls out of that calculation, combined with detailed maps of the radiation left over from the Big Bang, is 13. 8 billion years, with a margin of error of only about 20 million years. That precision is almost unbelievable for something so vast. It comes primarily from a European Space Agency satellite called Planck, which spent years mapping the cosmic microwave background, the faint afterglow of heat released when the universe was only 380,000 years old. Those measurements gave scientists a consistent, tightly constrained age, and for over a decade it held up against nearly everything thrown at it. That 13, 8 billion year figure isn't just one raw measurement either. It comes from a model called lambda CDEM, the working framework almost all of modern cosmology is built on. The name sounds technical, but the idea behind it is simple enough to state in one breath. Lambda stands for dark energy, the mysterious force pushing space apart and accelerating its expansion, while CDM stands for cold, dark matter, the invisible material that outweighs ordinary matter and holds galaxies together gravitationally. Under that model, the universe today is made of roughly 68% dark energy, about 27% dark matter, and only around 5% the ordinary atoms that make up stars, planets, and everything you can touch. Feed those proportions into the equations, calibrate them against the cosmic microwave background, and 13, 8 billion years falls out the other end. Every debate about the universe's age is really a debate about whether those underlying proportions and assumptions are exactly right, not a debate about whether the Big Bang happened or roughly when. It's also worth knowing this fight over expansion didn't start with Webb. In 1929, astronomer Edwin Hubble published observations showing that distant galaxies were systematically moving away from us, and that the farther away a galaxy was, the faster it appeared to be receding, a relationship now called Hubble's law. Belgian astronomer and priest Georges Lemaitre had proposed the underlying expanding universe theory a couple of years earlier, and today many astronomers credit both of them jointly for establishing that the cosmos isn't static. That single relationship, distance tied to recession speed, is the ancestor of every modern Hubble constant measurement, including the two feuding numbers, 67, 4, and 73, that are driving the current tension nearly a century later. The tools have become extraordinarily more precise. The fundamental disagreement about exactly how fast space stretches has, remarkably, never fully gone away. Then James Webb launched, and it changed what astronomers could actually see. Webb doesn't observe visible light the way Hubble does. It's built to catch infrared light, which matters because the universe's expansion stretches light waves as they travel across billions of years of growing space. A galaxy's light that started out as visible or ultraviolet gets stretched or redshifted into the infrared by the time it crosses the cosmos to reach us. The more a galaxy's light has been stretched, the further back in time astronomers are looking. That stretching is called redshift, and it's the single most important measurement in this entire story, so it's worth locking in once. Higher redshift number means older light, meaning a snapshot from closer to the Big Bang itself. Webb was built specifically to hunt for the highest redshifts anyone had ever detected, and it delivered almost immediately. Within its first year of full operation, astronomers using Webb identified dozens of galaxy candidates sitting at extreme redshifts, and follow-up spectroscopy, a more precise technique that reads a galaxy's exact chemical fingerprint rather than just estimating its color, confirmed several of them existed when the universe was only 300 to 400 million years old. That's less than 3% of the universe's current age. For comparison, if the universe's full history were compressed into a single calendar year, these galaxies would be visible in the first few hours of January 1st. Here's where things got genuinely strange, and where the real controversy started. These early galaxies weren't the faint, blurry, barely formed blobs that standard cosmological models predicted for such a young universe. Some of them were bright. Some were surprisingly compact and structured. and several appeared to carry far more stellar mass, essentially more built-up star material packed into them, than existing models of galaxy formation said should be possible that early. One of the researchers involved, Joel Leja, an astronomer at Penn State, put it plainly when a batch of these unexpectedly massive early galaxies was first announced. These objects were way more massive than anyone expected, based on everything astronomers thought they understood about how galaxies grow. MOEM Z14 isn't an isolated case either, and stacking a few examples together, purely as illustrations of the pattern rather than as separate proofs, makes the puzzle easier to picture. Earlier record holders like JWST Z14-0 confirmed at a redshift above 14 in 2024, and GN-Z11 identified years before Webb even launched using earlier Hubble data and later refined with Webb spectroscopy. Both pushed the observable boundary further back than expected at the time. In 2025, astronomers using Webb also identified an unusually large, well-organized rotating disk galaxy, nicknamed the Big Wheel, observed as it existed roughly 2 billion years after the Big Bang. Notable because fully formed rotating disks that size were assumed to need considerably longer to settle into shape. None of these examples individually rewrites cosmology. Together, as a pattern repeating across different research teams and different redshifts, they're why astronomers keep describing galaxy formation, not the age of the universe itself, as the area genuinely under strain. That single discrepancy, mature-looking galaxies appearing far too early, is the actual seed of every universe isn't 13, 8 billion years old headline you've seen. It's a real anomaly. It is not, however, proof that the age of the universe itself is wrong, and that distinction gets flattened almost every time this story gets retold online. To understand why, you have to separate what Webb is measuring from what headlines are implying. When a galaxy looks old, that word is doing a lot of quiet, misleading work. A galaxy can look old because it's unexpectedly bright. It can look old because it shows heavy chemical elements, materials like carbon, oxygen, and iron, that are normally forged inside multiple generations of dying stars, meaning enough time should have passed for several stellar life cycles to complete. It can look old because it's organized into a clear structure, like a disk or a spiral, rather than the chaotic blob you'd expect from a young, still-forming system. And it can look old because it's stopped actively forming new stars, appearing to have already burned through its youthful growth phase. Every one of those traits can suggest maturity. None of them, on its own, is a literal stopwatch proving billions of years have passed. What Webb has reliably found is galaxies that are unusually developed for their age, not galaxies that are provably older than the Big Bang allows. That's a crucial difference, and it's the difference between a genuine puzzle in galaxy formation and an actual crisis in cosmology. This isn't the first time this exact pattern of alarm has played out either. Back in 2023, within Webb's very first year of science operations, astronomers announced the discovery of 6 candidate galaxies that appeared to date back to roughly 500 to 700 million years after the Big Bang, and some looked, at first glance, almost as developed as the Milky Way. Coverage at the time called them galaxies that shouldn't exist. It made for a great headline. But as an illustrative example of how these stories tend to evolve, several of those original candidates were later re-examined with more detailed spectroscopy, the same follow-up technique used to confirm MOEM Z14, and some of the earliest, most dramatic mass estimates came down once better data replaced the initial rough guesses. That's not a failure of science. That's exactly how science is supposed to work. Loud initial claim, quiet, careful correction, more accurate final picture. The problem is that the loud claim generates 10 times the audience the quiet correction ever does. So if the 6 impossible galaxies story cool down after closer inspection, why does the tension keep resurfacing with new discoveries almost every year since? Because Webb keeps finding more of them, and the pattern hasn't gone away even as individual cases get refined. Each new confirmed early galaxy adds another data point to a growing pile of objects that are more massive, more structured, or more chemically mature than the standard model of galaxy formation predicted was achievable in the available time. No single galaxy breaks cosmology. A consistent pattern across dozens of them, however, is exactly the kind of anomaly that eventually forces theories to bend, and it's worth being clear about what bending a theory actually tends to look like in practice. It rarely means throwing out the Big Bang or starting over from scratch. More often it means adjusting assumptions about how efficiently gas collapses into stars in the universe's first few hundred million years, or revising how quickly the first generations of massive stars could seed a young galaxy with the heavier elements that make it look chemically mature. Those are technical, unglamorous fixes compared to a headline about the universe's age secretly changing, but they're the kind of fixes that have quietly absorbed similar anomalies before, without ever requiring 8 billion years itself to move. Now here's the part almost none of the sensational headlines mention, because it's less catchy but far more scientifically serious. There is a real, measurable, ongoing dispute about the universe's expansion rate, and it has a name, the Hubble tension. Two completely independent methods exist for measuring how fast the universe is expanding today, and they disagree with each other by more than they reasonably should. Now, the first method looks at the early universe. It uses that same cosmic microwave background data from the Planck satellite, feeds it into the standard cosmological model, and calculates an expansion rate of about 67, 4 kilometers per second per megaparsec, a unit that essentially describes how much faster galaxies appear to recede from us for every added unit of distance. The second method looks at the nearby present-day universe. It uses pulsating stars called Cepheid variables, whose brightness rises and falls in a rhythm precisely tied to their true luminosity, to calibrate distances to galaxies, then extends that ladder outward using exploding stars called Type Ia supernovae, which all detonate at a remarkably consistent brightness and act as reliable cosmic distance markers. That local method, run for years by a team led by astronomer Adam Rees, consistently returns a faster expansion rate, around 73 kilometers per second per megaparsec. Both sides of this argument represent decades of careful, cross-checked work, not a quick guess from either team. The Planck satellite operated from 2009 to 2013, and its cosmic microwave background analysis has since been independently checked using entirely separate instruments, including NASA's earlier WMAP probe and, more recently, the Atacama Cosmology Telescope, all landing in the same neighborhood near 67. 4. On the local side, the JWST team, short for supernovae H0 for the equation of state of dark energy, has spent years refining its Cepheid and supernova calibration, using data from Hubble and increasingly Webb itself, consistently returning values clustered near 73. 2 respected independently verified techniques, and they don't agree. The gap between 67, 4 and 73 might sound small, but statistically it isn't. Depending on which specific data sets are compared, the disagreement has been measured at anywhere from roughly 4 sigma to more than 6 sigma. In plain terms, sigma is a way of expressing how likely a result is to be a random fluke rather than a real effect. And physics generally treats 5 sigma as the threshold for calling something an actual discovery rather than noise. Attention above 5 sigma, sustained across multiple independent teams and years of refinement, is not a rounding error. It's one of modern cosmology's most stubborn open problems, and it's been intensifying rather than resolving. There's a third major cosmological survey, adding pressure from a different angle entirely, and it's arguably more disruptive to the standard model than either side of the Hubble tension alone. The Dark Energy Spectroscopic Instrument, DESI, has spent the past couple of years mapping the three-dimensional positions of millions of galaxies to measure how dark energy's push has behaved over cosmic history. Standard lambda CDM assumes dark energy strength is constant, fixed, unchanging forever. DESI's 2025 data release found something that unsettled that assumption. Evidence, at a confidence level in the range of roughly 3 to 4 sigma depending on which additional data sets are folded in, that dark energy strength may actually be evolving over time rather than sitting fixed at one value. If that holds up under further scrutiny, it wouldn't just tweak the Hubble tension, it would challenge one of the core pillars of the 13. 8 billion year calculation is built on in the first place. As of the middle of 2026, this result remains provisional and contested, with some independent teams urging caution about interpreting the current statistical strength as definitive. But it's a second, largely separate crack in the standard model running in parallel with the galaxy formation puzzle Webb keeps deepening. Webb was specifically expected to help settle this because it sees, with roughly 4 times Hubble's resolution, astronomers hoped it would reveal that the local, nearby measurements were being thrown off by something mundane, crowded star fields or dust interfering with the Cepheid brightness readings. Instead, Webb's sharper data confirmed the local measurements were solid, closing off what had been one of the most obvious potential explanations for the discrepancy. At the January 2025 American Astronomical Society meeting, astrophysicist Dan Skolnick didn't hedge about what that meant, calling the disagreement a crisis outright. Then, in December 2025, an entirely independent technique added more weight to one side of the argument. Researchers measured tiny time delays in light from gravitationally lensed quasars, extremely bright, distant objects whose light gets bent and split into multiple images by the gravity of a foreground galaxy, creating slightly staggered arrival times that can be used to calculate the expansion rate without relying on Cepheids or supernovae at all. That method landed on the side of the faster, local expansion rate, deepening the mystery rather than resolving it, exactly the opposite of what everyone had hoped for. Then, in early 2026, the tension sharpened even further. A global collaboration of researchers, including scientists from the Harvard-Smithsonian Center for Astrophysics, published what they described as the most precise local measurement yet, achieved by building what they called a community-wide distance network. Instead of leaning on Cepheids alone, they combined 3 separate stellar distance techniques: Cepheids, a method using the brightness of aging red giant stars, and pulsating stars called Mira variables, cross-checked across data from Hubble, Webb, and the Keck Observatory. The result came in at 73, 5 kilometers per second per megaparsec, with an uncertainty of less than 1%. That level of precision effectively ruled out simple measurement error as the explanation for the entire discrepancy. Around the same time, a separate telescope, the Atacama Cosmology Telescope, released its final cosmic microwave background map, and it lined up closely with Planck's early universe number, reinforcing the other side of the divide instead of splitting the difference. 2 increasingly confident camps, standing further apart than ever. There's actually a third, older way of estimating the universe's minimum age that rarely makes headlines, but quietly keeps everyone honest: counting the ages of the oldest known stars. Certain ancient globular clusters, tightly packed balls of stars orbiting our galaxy, contain stars whose age can be independently estimated from their brightness, color, and how far they've burned through their nuclear fuel, using stellar physics that has nothing to do with cosmic expansion or the cosmic microwave background. Those independent stellar age estimates consistently come out at around 13 billion years, comfortably fitting inside the standard 13, 8 billion year timeline with room to spare. That's an important sanity check, because whatever the final resolution of the Hubble tension turns out to be, any accepted age for the universe still has to be old enough for those individual stars to have had time to form and age the way their own physics says they did. It's a floor, not a ceiling, but it's one more independent line of evidence that a wild swing like 26. 7 billion years has to somehow account for, and one more reason the mainstream shift under discussion is measured in a single-digit percentage, not a factor of 2. So what does any of this actually do to the age of the universe? This is where the math gets genuinely interesting instead of just alarming. The age calculation and the expansion rate are directly linked, because a faster expansion rate implies the universe reached its current size more quickly, which, all else being equal, means less time has passed since the Big Bang. If the faster local expansion rate ultimately turns out to be the correct one, the simplest versions of the standard cosmological model would nudge the universe's age downward from 13, 8 billion years towards something closer to 12, 5 to 13 billion years. Notice the direction of that shift. It's downward, not upward, and it's a shift of less than a billion years, not a doubling. That's about a 5 to 9% adjustment, meaningful for cosmologists, arguing over precision to the decimal point, but a world away from the kind of everything you know is wrong framing that spreads across social media. As of the middle of 2026, the honest current status of the field looks like this. The 13, 8 billion year figure is still the number every major space agency and peer-reviewed cosmology paper uses as the working standard. It has not been officially revised, but it is more actively contested than at any point in roughly 2 decades. With the Hubble tension unresolved, the early galaxy anomalies from Webb still unexplained, and new precision measurements arriving almost every few months that narrow the error bars without narrowing the disagreement itself. Scientific institutions have responded by throwing more tools at the problem rather than picking a side. A European Research Council-funded project with the deliberately blunt name RedH0T has assembled teams whose entire job is to aggressively hunt for hidden biases in existing measurement methods, essentially trying to break the results on purpose to see if they hold up. Meanwhile, the European Space Agency's Euclid mission is compiling an independent map of the universe's large-scale structure, expected to weigh in with results later in 2026, offering a genuinely third method that doesn't rely on either Cepheids or the cosmic microwave background. What would it actually take to close this out for good? Not one dramatic announcement, most likely, but a slow convergence from several unrelated directions at once. If Euclid's structure map lands closer to the early universe number, that weakens the case for new physics and points back towards some overlooked systematic error in the local distance ladder. If it lands closer to the local number instead, that's a third independent confirmation, on top of Webb and the lensed quasar method, and it becomes very hard to keep dismissing the faster expansion rate as a fluke. Gravitational wave astronomy offers a completely separate check as well. When 2 neutron stars or black holes merge, the resulting ripple in space-time carries its own built-in distance measurement, entirely independent of Cepheids, supernovae, or the cosmic microwave background. As detectors improve and catch more of these mergers with visible counterparts, that method is expected to add real statistical weight to one side of the argument within the next several years. Cosmology doesn't usually get resolved by a single knockout observation. It gets resolved when enough independent methods, built on different physics and different instruments, all start pointing the same direction. Now, alongside that mainstream, still unresolved tension, there's a second and much more radical thread that regularly gets tangled into these headlines, and it deserves to be presented honestly as the outlier that it currently is. A physicist at the University of Ottawa, Rajendra Gupta, published a model this year arguing the universe isn't merely a billion years off, but roughly double the standard estimate, landing at 26.7 billion years old. His approach blends standard cosmic expansion with two much more speculative ideas, a variant of an old concept called tired light, where light loses energy gradually as it travels enormous distances rather than purely from cosmic expansion, and a framework in which fundamental constants of physics are allowed to shift slowly over cosmic time rather than staying perfectly fixed. Combine those two mechanisms, and you get a model where the universe's clock effectively runs differently at extreme distances, stretching the calculated age far beyond the familiar figure and, in the process, comfortably explaining away the puzzle of Webb's unexpectedly mature early galaxies, because in that model they simply had far more time to form than the standard timeline allows. The tired light half of that idea is worth a brief pause because it isn't new, and understanding why most cosmologists remain skeptical of it says a lot about how these fringe proposals get evaluated. The original tired light concept dates back nearly a century to the years right after Hubble's redshift discovery, when some physicists proposed that light might simply lose energy on its own as it crosses vast distances, mimicking the redshift we now attribute to cosmic expansion. It fell out of favor decades ago because it fails several independent tests. Real expansion passes easily, including predictions about how the light from exploding supernovae should stretch out and dim over time. Reviving a version of that mechanism, even a modified one paired with shifting physical constants, means clearing all of those same old objections again, not just accounting for Webb's early galaxies. That's the steep, largely unmet bar Gupta's 26. 7 billion year model is up against. It's important to be precise about what that proposal actually is and isn't. It is a real, published, peer-reviewed piece of theoretical work, engaging seriously with genuine observational puzzles. It is not a replacement for the standard model that the physics community has broadly accepted, and it directly contradicts extremely well-tested assumptions, including the idea that fundamental constants are, in fact, constant, an assumption that underpins enormous amounts of confirmed everyday physics. A model that fixes one anomaly by loosening dozens of other well-established results faces a very high bar before it gets adopted. And as of today, this one hasn't cleared that bar. It's a serious hypothesis worth tracking, not a rival consensus, and treating it as though it already displaced 13. 8 billion years badly overstates where the science currently stands. It's worth pausing here to notice the human side of this story, because it explains why the misleading headlines spread as easily as they do. For most people, the universe's age changed sounds like a headline about certainty being overturned, a fixed fact suddenly proven false, which is inherently more shareable than scientists still disagree about a measurement by about 8%. But that framing badly misrepresents what real scientific uncertainty looks like day to day. Cosmologists aren't confused about whether the universe had a beginning or whether it's been expanding for billions of years or whether Webb's data is reliable. They're refining a number down to fractions of a percent using two independently powerful techniques that keep landing in slightly different places. And they're doing it in public through published papers, competing observatories, and open disagreement at major conferences, which is exactly what functioning science looks like when it hits a genuinely hard problem. The uncertainty itself is the sign the system is working, not evidence that it's broken. That misunderstanding has real downstream consequences beyond a misleading thumbnail. When headlines repeatedly claim the age of the universe has secretly changed, and then nothing visibly changes in the following weeks, it quietly teaches audiences that scientific institutions are either withholding something or don't actually know what they're talking about. Neither is true here. What's true is slower and less dramatic. Two well-tested measurement techniques disagree by about 8%. A separate dark energy survey is hinting the standard model might need an update to one of its core assumptions. And a wave of unexpectedly developed early galaxies is forcing theorists to reconsider how quickly galaxies can actually form. Every one of those threads is being investigated in the open, with published data anyone can check, which is the opposite of institutions hiding an inconvenient truth. There's also a quieter irony sitting underneath all of this. Webb wasn't built to challenge the age of the universe. It was built to look further back and in sharper detail than anything before it, specifically so scientists could stress test their existing models against real data instead of theoretical guesswork. Its IS-6, 5-meter primary mirror, assembled from 18 gold-coated hexagonal segments, collects more than 6 times as much light as Hubble's 2. 4-meter mirror, and its instruments are tuned specifically for the infrared wavelengths that the most distant, most redshifted galaxies actually arrive in. That combination of light-gathering power and infrared sensitivity is precisely why Webb, and not Hubble, was the telescope capable of confirming something like MOMZ14 at redshift 14, 44 in the first place. Finding early galaxies that don't fit predictions isn't a failure of the telescope or a scandal in cosmology. It's the entire reason. An instrument this expensive and this sensitive was built in the first place. The tension it's exposing between early universe and local measurements existed before Webb ever launched. Webb just gave scientists sharper tools to confirm the discrepancy is real, rather than a measurement error waiting to be explained away. So where does that leave the number 13? 8 billion years right now, in the middle of 2026. It's still the figure NASA uses in its own recent releases, including the announcement confirming MOMZ14 as the most distant known galaxy. It's still the figure taught in classrooms and cited in peer-reviewed papers as the working standard. But it now sits inside a wider band of genuine uncertainty than it has in 20 years, bracketed on one side by a faster local expansion measurement that, if fully validated, would trim it down toward roughly 12, 5 to 13 billion years, and challenged on a completely different front by unresolved puzzles about how galaxies as massive and structured as the ones Webb keeps finding could form so early. Neither of those pressures has broken the standard model yet. Both are being actively, rigorously tested by multiple independent teams and missions right now, with Euclid's structure map and further precision distance ladder results expected before the end of this year. So did James Webb catch the universe's age changing? Not in the way the headlines want you to believe. The official number hasn't moved, and no credible finding has proven 13. 8 billion years wrong. NASA is still citing it in releases as recent as January 2026. Independent stellar ages still fit comfortably inside it. And the one serious rival proposal claiming to double it, Rajendra Gupta's 26, 7 billion year model, remains a contested minority position rather than an accepted correction. What Webb actually caught is something more valuable than a single dramatic number changing overnight. It caught the seams in our current model of the cosmos starting to show. Real disagreement between trusted, independent measurement techniques that keeps sharpening rather than resolving. A dark energy survey hinting that one of cosmology's core assumptions might need revising, and a growing set of early galaxies that grew up faster than anyone predicted they could. If the faster local expansion rate is eventually confirmed beyond doubt, the number most likely settles somewhere between 12, 5, and 13 billion years. A real but modest correction, not the dramatic reversal the title of a viral headline implies. That's not the universe's age quietly changing behind our backs while nobody was allowed to check the math. That's the leading edge of how the actual number, whatever it ultimately turns out to be, gets earned in public through disagreement, and through exactly the kind of uncomfortable, unresolved tension that real science looks like while it's still being done.